All right, welcome back to part 2 of Thursday's lecture. Picking up where we left off, charge at an interface of two wires of different materials. So we would have a wire made out of metal 1 connecting to a wire of a different material metal 2. All right, so the radius of wire 1 is equal to the radius of wire 2. The U of wire 2 is much, much smaller than the U, the electron mobility, of wire 1. And the electron density of wire 1 is greater than the electron density of wire 2. And the question we want to go after is, current I is running this way. Okay. So what is the charge where the metals meet? All right, so to go after this, we're going to use node rule. So I1 is equal to I2. So we've been given electron current, so we're going to stay in terms of electron current. So this implies N1 NaU1 E1 is equal to N2 U2 E2. So we know that the areas are the same. We know N and U are different, and we would then infer that E1 and E2 are different. So we'd get that the electric field from metal 2, this one, is equal to N1 U1 over N2 U2 times E1. And this makes sense. E2 is larger than E1. All right, so now let's do a Gaussian surface. So, color I haven't used, we can draw a Gaussian surface along here. Okay, so we know that we're going to have, so E2 is right here, and E1. So there's our Gaussian surface. And so any change in the surface must be at this interference, because we already know that metals are zero. So we're looking specifically at what's going on at this interference, or we haven't yet discussed how to handle. Okay, so let's apply Gauss's law. Surface integral E dot dA is equal to Q enclosed over epsilon naught. All right. So the assumptions that we're going to have. So E is parallel to the wire and uniform in the same material. So we know it's different from material 1 to material 2, but within that same material, it's the same. Okay, so let's go after flux. So the outer surface, flux is equal to 0 because of that parallel property. The top end, which would be metal 1, the flux is equal to E1 pi r squared cosine of 0 is equal to E1 pi r squared. And the bottom end, metal 2, flux is equal to E2 pi r squared cosine of 180 is equal to minus E2 pi r squared. So previously we've been looking at a wire made out of the same material. These two had canceled. That's no longer the case. So we have the surface integral E dot dA is equal to 0 plus E1 pi r squared minus E2 pi r squared. And so Q enclosed is equal to epsilon naught E1 pi r squared minus E2 pi r squared. And so Q enclosed is equal to epsilon naught I 1 over N1 U1 minus 1 over N2 U2. And we can see Q enclosed is negative. And that makes sense because the interference should be negative to increase the electric field from metal 2 and decrease the electric field at metal 1. So these are the parameters, again, that we started with. All right. So you might be saying, okay, so we have Gauss's law for electric fields, but what about those magnetic fields? Well, it turns out we've got an expression for that too. Let's look at Gauss's law for magnetism. All right, so there is a big difference between electric objects and magnetic objects. And this stems from the simple fact that there are no magnetic monopoles. Nope, 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 no, no. Okay, so you would never have a magnetic field that looks like this. Wrong. Does not exist. Okay. That being said, we can get out of this Gauss's law for magnetism. So, since we're only ever going to be dealing with dipoles, B dot N dA is equal to 0. We do not get the same flux patterns with magnetic fields that we get with electric fields. However, if you want to do something really cool, take a good old-fashioned Griffiths electromagnetism class, and you will get to do some of Maxwell's equations as though the magnetic monopole exists. And there's a solution for that. It's just theory, though, so it's all fun and games. Okay, so moving on. So 21.6, patterns of magnetic fields. And we're going to deal with Ampere's law, which is a little bit more exciting. All right. So, just like Gauss's law and Coulomb's law are related. So is Ampere's law. To Biot-Savart. Doesn't that bring back memories of the SAT? If you took it. All right, so we are already pretty familiar with patterns of magnetic fields, but let's just quickly review. So here's one we've seen before. So that curly magnetic field. So it's curly B field. So what could make this curly field here? Well, magnetic fields are caused by moving charges, and this field is likely caused by a current carrying wire. With I out of the page. If it was going this way, I would be into the page. All right. So we know how to relate magnetic field patterns to their causes, just like electric fields. We've been doing that for a while. So let's quantify these patterns. So we already know, using Biot-Savart, how to quantify a field from a current carrying long wire. So quantify B from a wire with I, and it's going to be related to R, which is the distance. I should say related, use the proportionality sign, from the wire. Okay, so, and what we have is that B wire is approximately mu naught over 4 pi 2I over R. And we got this from chapter 17. So there's our wire, there's our R, here's our field as a result of the wire. Okay, easy peasy. Now, let's think about doing this in a new and different way. Let's think about adding up the magnetic field around the wire. So what you may want to do is take a path, start here, walk around, and then just sort of pick up all of the magnetic field contributions as you go around. So you're adding them up, or you are integrating all along this round trip path. So what that is you're doing this. Taking the sum of all the magnetic field contributions as you walk around in a circle, sort of picking them up and adding them together. So this is along a round trip. And again, those of you who are not in the calculus-based class, DL is just going to be the length of your path. So we're just doing geometry. So in this case, we looked at a circular path around a wire. So if we do that for this setup, so B dot DL is equal to mu naught over 4 pi 2I over R. Put out in front of the integral, these are all going to stay the same. And you're going to look at it around the round trip DL. So, a couple things. B is parallel to L, and R is constant. So, B dot DL is equal to mu naught over 4 pi 2I over R. If you walk in a circle, you just traverse distance 2 pi r. And so this is equal to mu naught I. So going back to our picture, here's the current. It's coming out. Here's R. You're just walking along. We can see R and the magnetic field are parallel to each other. You're just picking up all of these contributions by going in a circle. So we now have Ampere's law. B dot dl is equal to mu naught times the sum of the current inside the path. So in words, the path integral of the magnetic field is mu naught times the current passing through the region enclosed by the path. And just like Gauss's law, it's only what's on the inside that counts. So if the current is outside of your path, 0. It has to be inside your path. And just like whether or not you're choosing Gauss's law or Coulomb's law, you make this choice based on which is easier to calculate. So Ampere's law is the more pure of the two expressions. It's always true. It's even true relativistically. But sometimes Biot-Savart is easier to calculate. So choose what's easier because you're going to get the same answer no matter what. And remember, there's no cookies for making things harder on yourself than they need to be, and you're more likely to get something wrong. All right, so let's compare Ampere and Gauss. Well, not the people, the laws. The laws. So for Ampere, B needs to be parallel to the path for a non-zero result because it's a path integral, not a surface integral. And for Gauss, the electric field needs to be perpendicular to the surface for a non-zero result. So you want parallel magnetic fields and perpendicular electric fields if you want to get a non-zero value. All right, so how do we do Ampere's law? So let me give you some steps. All right, so if you're going to do Ampere's law, first, you need to choose a closed boundary. It's mathematical. And your choice. Make it easy. Okay, 2, pretend the boundary has a film over it. Like a little bubble film or plastic wrap. And then go around the boundary. Clockwise, adding up B dot dl. And then you add up all the currents that pierce the film. So you need to sum all the magnetic field contributions, and then you need to sum up all the current contributions. So Positive currents come out. Negative goes in. Then use Ampere's law. So B dot dl is equal to mu naught times the sum of all of the currents enclosed. And there you have it. Those are the steps for Ampere's law. Okay, so now that we know the steps, let's try it out. So this time we're going to look at a long, thick wire. All right, so far we've only done thin wires. So we know B sub A for a thin wire, and that we had to make that assumption to do that calculation. So we already actually have a problem where Ampere's law is actually going to be far more straightforward than using B sub A. And that would be the integration method that we've been using previously. Still highly effective and sometimes the easier of the two. So for this one, we're going to go after Ampere. Ampere, take it away. All right, so here's our wire. See, it's nice and thick. We've got some current. Now we're going to look at some distance r. Here's the path. And then, of course, we've got our magnetic field hanging out, curling around that wire. There we go. Beautiful. All right, so let's break this down. So the path integral we're going to walk in a circle. And so you're going to have B dot dl is just B 2 pi r, because you're just going in a circle. So really, we haven't done any calculus. We are just doing geometry and algebra. All right, so by symmetry, we know B is constant in magnitude. And it's also parallel to DL. So again, with these types of things, you do want to double check your concepts. So now let's think about the amount of current that is rushing through our area. And in this case, it's really easy. We just have, if we were to put a little film over here, you would just have one bit of current coming through, which is just going to be the current from the wire here. So it's only going to be pierced one time. Okay, so current coming through is just I from the wire. Now, if you had two wires going through that, it'd be a different story. So from there, you have B 2 pi r is equal to mu naught I, because, you know, 1 plus nothing else is just that. So B is equal to mu naught over 2 pi r is equal to mu naught over 4 pi to I over r for a thick wire. And so we see we actually have gotten the same as the B sub A But we needed a different way of thinking about it. So we had to basically say it was infinitesimally thin, and now we see that really the thickness of the wire is not what's important. But what matters is how we think about these problems. So even if you get the same result for the two, which you will, recognize that the methods are different. So you need to do the method that is required. Okay, so now let's play this game with a solenoid. Now we get to have multiple currents going through. Okay, so we all remember a solenoid, I hope. So we've got all of these wires, got current going through. I'm going to look at some length, L of the solenoid. It's got relatively uniform magnetic field going through. Okay, so let's look at a segment within the wire. So we'll look at some segment with length D. So this is going to be our path that we're going to walk around. And so the nice thing about solenoids, as I said, but now I'll write out, magnetic fields are fairly uniform in a solenoid, as long as you are far from the ends. So let's use that to our advantage. And if you remember, N is the number of loops. I believe one of you counted up the number of loops on one of the solenoids I passed around. L is the length of the solenoid. And there are N over L times D wires piercing our area. And each one of these is going to have some current, I, going through it. Okay? So let's break this down. So we've got B dot dl is equal to BD. That's the length. Now we need to go after I total. Okay. So the wire goes through. Oh, and at the ends, I should mention, the ends are perpendicular. So therefore, you have zero contribution on either one of these two ends. It's just D. And we can see that D here, this is the part we're interested in. Okay. So the wire goes through NL times. So I total is equal to N over L DI. So we have BD is equal to mu naught N over L D times I, and these cancel, which is good because you don't want this expression to depend on something arbitrary that you have introduced. B is equal to mu naught over N I over L. So much easier than the integration method that we used last time to go after the magnetic field of a solenoid. So beautiful. Okay, so let's go on to one of my favorite shapes, a toroid, which is a donut. Add a toroid. a donut. So essentially, we're going to take our solenoid and we're going to bend it in on itself. So you'll have all of these loops of wire going around, and then you get a donut. So a solenoid folded so that the ends meet. And you get a torus. So and then you have all these loops of wire, which would of course be much, much closer. Okay, so if we were to look at a little cross section, so we're going to see for each one of those loops, you would have some I that would be piercing it. And you've got the magnetic field going around from the torus. Should really do different colors. Our magnetic field B, and here are the eyes that are piercing. I'm obviously not drawing all of them, but you get the idea. So we now have the current piercing through a film several times, and you've got your magnetic field B. So there are N loops that pierce the area. So you have B dot dl is equal to B times 2 pi r, so you're still walking in a circle. B is still constant and always parallel to delta L, and it's a circle. So basically we've just gone for a little walk right through there. Okay, so moving along, then we have B 2 pi r is equal to mu naught n I. Beautiful. So the magnetic field of a toroid is B is equal to mu naught Ni over 2 pi r, and B is once again proportional to 1 over r. I mean, can you imagine solving that using Biot Savart? Whereas Faraday's law, like 2 easy steps, and we were there. So this brings us to Maxwell's equations, 2.17. So we've developed 3 new equations in chapter 21. They're very important. We have Gauss's law for electricity, Gauss's law for magnetism, and Ampere's law for magnetism. All right, so we kind of have Ampere's law for electricity in that a round-trip path integral of an electric field by a stationary or slow-moving charge is 0. So you could say we're somewhat there. And these equations are the basis for Maxwell's equations. And we can write 2 out fully as it stands. So, Maxwell's equations. And one of them we do not have the complete expression of yet. So E dot n hat dA is equal to the sum of Q enclosed over epsilon naught, which is Gauss's law, for electricity. And then we have B dot n hat dA is equal to 0, which is Gauss's law for magnetism. And then we have E dot dl is equal to 0, Faraday's law, and this is incomplete. We need to get to the next chapter to get there. And we have B dot dl is equal to mu naught times the sum of the current inside, which is Ampere's law. And this is also incomplete. We still have some pieces to put into place, but these are the equations, in part, that we have been building towards all semesters long. This is the basis of everything we talk about in Physics 2. All right, I will see you next week where we will start chapter 22.